Okay, so
GSAS-2 or just
I'm going to go over GSAS-2, pyGSAS. So if you have that downloaded and you want to follow along, great. Otherwise, you should be able to follow these steps, no problem. I've given the steps on how to do it. So for example, if you go to the Rietveld Refinement thing, which is posted, it says things to do before your refinement, like download and install GSAS. Make sure that your XRD data is in a format that GSAS can read. It needs to be one of these three types, RAW, FXYE, or GSAS. You should run a calibration on your instrument to make sure that you know what the zero of your instrument is. I'll talk about some of this as we go. But this is stuff you do before you do your refinement, right? Then when you're ready to do your actual refinement, here's the steps you follow. So first off, you're going to open up GSAS, and you're going to open a new project and save it with a new name, right? So wherever you've got your GSAS at, I think I've got mine on my desktop, I can get to it. GSAS-II should look like that. If you've installed it, it usually puts an icon on your desktop. Otherwise, you can launch it from the folder where it's saved. All right. So I've got a brand new thing. This is the GSAS, sort of what you're going to look at. It's got a series of windows, right? The first one over here is called the data tree, right? It says up here GSAS-II data tree. And it's the one that you're going to go back to over and over. And as you click things in the data tree, this other window will change on its own. And it's a little bit obnoxious, but the data tree is the one that won't change. It's nicer if you have a bigger screen for this, but we can do it on laptop too. So let's open a new project, or just do a save project as, and let's save this where we're working on. I've got mine in my G users, G2 Conda. That's what it's built out of. GSAS-II, my work, and let's do a new one. We'll call it in-class example. Well, we'll just go to the one that's already here. All right. So I'm going to put it in the 25 degrees Celsius. So you guys have this Cobalt 304 example folder. That's what I just put up on the Rietveld Refinement. When you open that up, if I go back to this parent folder, you'll notice that it has inside of it a bunch of different folders for temperatures, right? And substrate fit, right? So open up the first temperature, I2-25C. That means it's the first scan that we ran, and it's at 25C. So it's room temperature scan, right? Open this up, and we're going to create a new one. So let's call this Feb1, right? It's going to save it automatically as a .gpx file, and that's something that it will know opens up in GSAS-II, right? So now we've got a new file. Terrific, right? Again, when you click on different things here, these other windows sort of jump around and change on their own. It's a little bit obnoxious. They just change on their own, okay? So let's go to our guide and figure out what our next step is. Our next step is, now that we've got this, we've got it saved. We talked about what the data tree is. Next step is we need to import the powder data, right? So you would have already run your X-ray diffraction pattern. You've already saved it in the format you want. Now you need to bring that data in. So the way we do that is you go to our data tree, and we go to import powder data, and you tell it what it is, right? So ours is in a GSAS powder data file. It could be in a lot of different things. Like it can read Panalytical and some of these other things. I always just save it as a GSAS file, right? And I'm in the Cobalt example and in the subfolder, the 25C folder, and there's only one powder file there, right? It should be there for you guys. Hit that. This is, I think, a raw file. Hit OK. It says, okay, do you want to import this? Tell it sure. It then immediately prompts you. It says, choose instrument parameter file for this, right? So when you ran this, you should have saved an instrument parameter file when you did your calibration. If you don't have one of those, you can create one. We have one. You go back to the parent folder, and if you scroll down, here's our Expert O2 with cobalt radiation parameter file, right? So as soon as we add that, we have a new item in our data tree. This powder tab thing wasn't there before, right? And so now that that's there, this window that shows the pattern pops up, right? So let's go to our window and see what we need to do next. We've added the data, right? We started with 25 degrees Celsius, which is our first sample, as we're going to heat the sample up and keep on running it, right? pyGSAS automatically asks you about the instrument parameter file, and it creates this powder item in the data tree. So now that we've got that done, we need to tell it a little bit more about the diffractometer type, because this wasn't set correctly in the instrument parameter file. So let's jump over to our data tree. And now under the powder, meaning we're going to talk about this specific histogram, the scanned actual data, we're going to go to instrument parameters. Sample parameters. Right here, sample parameters. And there's lots of information. You can name it. You can call this, like this was done at MIT. I could call it the MIT Cobalt X-ray machine, or whatever you want to do, right? You can name it. But more importantly, you have to make sure you're using the right diffractometer type. This was a Bragg-Brentano geometry, so I have to change that to Bragg-Brentano. You can put in the goniometer radius. I think it was like 180 millimeters on this machine. 200 is pretty close. I'm just going to leave it put because I know that it works if I leave it at 200. But if you know what the goniometer radius on your machine is, you can put that in, and technically it will make it a little better. We're going to turn off histogram scale factor for a moment. That will be checking these little boxes. That turns on and off variables that will be used in the refinement. The reason why we're going to do that is because right now, because we're going to turn on a scaling parameter elsewhere that has to do with individual phases. I'll show you what I mean by that in a moment. And we can leave the rest of this alone for right now. If right now we can leave that all alone. Okay, so we go to our next step. We changed it to Bragg-Brentano. Now it says go to the data tree / instrument parameters and make sure that the radiation wavelength is correct. So we go to our data tree. Now we're going to go to instrument parameters. And our instrument parameter file didn't tell it correctly to use cobalt radiation because it still thinks we're using copper. So go ahead and select cobalt radiation. Yeah, the wavelength is now 1.78, so that's now cobalt. That's the actual radiation. If you try and refine it with the copper radiation, you're going to get it won't ever fit, right? Because it's not going to satisfy Bragg's law. So tell it the right radiation. There's a lot of other information here that we'll talk about later. For right now, we can leave it though. Let's go to our next step. It says unclick the histogram for I already did that. Other things like sample displacement and transparency, we're going to adjust later. We can leave them alone for now. Okay, we're almost ready. We've got our histogram, we've got our data there. Now we need to introduce the phase that we're going to calculate the pattern for so that we can compare the two. So we have to import a phase. So go to your data tree. You're going to go up to import, and you're going to add a phase from a CIV file. It can read it from lots of other stuff. It can read it from other GSAS files that you've been working on. If you've already got a phase in there, it can read it from there. What we're going to do right now is just CIV file. So again, it's not in the individual folder where we're working. It's up a folder above, and we've got two phases we want to import. So let's add the spinel phase. It asks you some information about it, wants to make sure it's correct. You can name it something else if you want. We're just going to add it. And it asks you to associate it with a histogram pattern, meaning an XRD data set. There's only one XRD data set here. You could refine multiple types though. If you ran this in the lab and then you sent that same sample to like the Argonne National Labs or wherever and you did synchrotron, you could refine the same structure off of both patterns, right? Which is really a powerful tool. You could do neutron and X-ray at the same time. So right now we only have one data pattern to fit it to, so we're just going to click the one, but it could be multiple patterns that you're fitting the same structure to. Got to make sure that all other experimental conditions are the same. Height, temperature, all things like that. Okay, so now that added a new item to our data tree. Before we had the basic stuff for refinement, we had a powder tab that talked about the actual data. Now we have our first phase. So let's add the other phase. Same process, phase, import from CIV file. We're going to scroll down, we're going to add the rock salt phase. We can change its name. Again, tell it what histogram to work with. And now we have two phases in our phase item of our data tree. Okay, so let's go back over here, see what it says to do next. Okay, we've imported these. Okay. It says our next step, step number 7, it says go to the data trees, phases, and then individual phase. And what we're going to do is we're going to turn on individual scale factors. So again, let's go to data tree right here. Click like the Cobalt 304. We could eventually turn on things like unit cell, but let's leave those off for just the moment. Just go to data. And first off, do you want to use the histogram? Yes. And do we want to scale it right there? See that phase fraction? Right now, before you click that, it says 100% of the phase that's in your sample is that phase. And if you have two samples, 100%, 100%, it says that there's equal ratios of those both. But there's no reason for us to assume that we have a 50-50 mixture of spinel and rock salt. In fact, we want to be able to refine it. We want to figure out what exactly is the ratio. So you need to click that box so that it will refine it. Okay? So we're going to do the same thing with cobalt oxide, the rock salt phase. Click that phase fraction. Now that's refinable. So I think we're almost ready to refine it now. Okay, we did step 7. Almost ready for the refinement. Last thing you have to do before you do your very first refinement is you go to data tree, controls, and you set the number of iterations, right? Rietveld refinement goes through a bunch of steps and it gets closer and closer towards the right structure by changing things a little bit at a time. So you're basically saying how many times do you want to allow it to change something before you stop it. And 10 is a good number. You can make it to 100, but the likelihood of it doing something wrong and getting out of control is higher, right? So do smaller steps is a good idea. So come up here, again in the data tree, controls. You can tell it what type of, you shouldn't have to mess with this, but technically you can change how it does its regression. We're not going to bother with any of that. but we are going to tell it to do 10 cycles at a time. And now it's ready. We can go up here to calculate and tell it to do a refinement. It'll spit out these numbers. See, it did that really quickly, right? I don't know if you saw those numbers. It started out as it said RW, that's the weighted residual, that's the leftover. I think we talked about this briefly in here. Basically, it takes the actual pattern, it calculates the pattern, it subtracts the difference, and says how close was it? Is it 100% off? Is it 0% off? Is it a perfect fit or just the worst possible fit, right? So after running 10 cycles, our weighted residual is down to 16.2%. That's really good for your first run. That's really good. That means that our starting phases were a pretty close match to what the actual phase must have been, because it got a pretty good fit. So it'll ask you, do you want to load these new results? If for whatever reason you run this and it's going up, it goes up to like 50 or something, that means something's terribly wrong. You don't have to accept the results. You can cancel it and it'll throw out the proposed changes and it'll go back to the structure before you hit the refine button. But we want it to go back to it because 16 on your very first run is great. That's a pretty good fit. So now we can take a look at it. We can see how well we're fitting. To do that, go ahead and click the phase box and then hit the powder item, right? That'll create this nice image for us to look at. So if I take this, make it a little bit bigger, what you're seeing here is the following. Make sure that's home, right? You can hit the home button there. First off, you see a bunch of information. The tiny blue dots, that's your actual data you collected. These little vertical hash marks, that represents where you expect to see a reflection for the two different phases, right? You can see the legend up there. So the blue is for the rock salt, red is for the spinel. That's where you expect to see phases. Yeah, Garrett, question? So click one of these in the phases first, okay, and then click the powder up here on the data tree. Click right there. If you click that thing, that will make this thing automatically pop up. If it's too zoomed in, come over and hit this home button, and that will make it zoom out. Okay. So now let's zoom in and see actually how is it fitting, like what's going on here. You hit the zoom button right here, and go ahead and just drag an area. I like to drag kind of the whole thing to see the whole error, right? So we see a couple things. First off, there's this red line. That's your background. So we didn't actually go in and touch the background yet. That's something that you can edit. And sometimes you've got a weird background, like, is it, your name again? Ian. Ian. He's working on a material that has amorphous material in it, right? It's got some crystal and some amorphous. Amorphous puts a really nasty background. It's like this big funny bump. And right now, this is pretty much a flat background, that red line. But you can add some terms. It's just a polynomial fit, and you can make it fit that background. And sometimes you need to do that. For right now, we're clearly getting a pretty good fit because our background's pretty flat. You see there's the data points, and then you see the green line, the dark green line. The dark green line is the calculated pattern, assuming the two phases that we put in and all the instrument information. And you can see that then if you took the blue sort of like plus signs and minus the green, you get this teal line. The teal line is your error curve, right? So some things it fits okay, and some things not fitting at all. Let's take a look right here. This data has no calculated pattern that goes there. So if you take this and subtract the background, you get this error. You get a pretty monster error there. That's because there's another phase here that we're not accounting for. It's actually the substrate. Our sample was a little bit transparent. It was seeing the substrate. And I don't know what the substrate was, so I'm gonna talk to you about what do we do with that. If you don't know what the substrate is, you need to can you just delete the second and ignore it? That's one option. Or you can you can make the background fit it arbitrarily. We're gonna show you both options. Okay? But that's what you're seeing here. So basically we're fitting it pretty good, right? The actual peak and our calculated peak is not a bad fit there. Basically our calculated peak is too skinny though. It needs to be a little bit broader. So the shape of the peak isn't right. And if you zoomed in, you'd see that the actual position's not exactly right either. Like let's zoom way in on this. Actually, that one's pretty good. Let's go out and find another one. I think some of these don't. Yeah, like take a look at this one. Our calculated peak position and our observed peak position is not quite right. That's fine. That just means that the lattice parameter in the CIV file, wherever I downloaded it from, isn't the exact same lattice parameter in my material that I'm looking at. That's fine. Temperature affects the lattice parameter. Stoichiometry and composition affects the lattice parameter. It's okay to have to refine it a little bit. So we got a pretty good fit, but we could actually go ahead and go to our phases tab right now, and we could click refine unit cell for both of these two phases, and it's going to get better because it's going to move those peaks around a little bit. So let's do that. Let's hit. I'm probably getting ahead of myself in the. Yeah, I'm getting ahead of myself. That's all right. So we can go ahead and run it again. Go to our data tree, calculate, run it one more time, and we were at like 16 before. Now we're down to 14. So it got a little bit better. When do you stop? if you remember, you want your weighted residual to be less than 10%. You'd like your calculated pattern to be within 10% of your observed pattern. That's lower is always better, but that's sort of, I don't like to publish anything and say that we did Rietveld refinement if we don't get that below 40%. And that's a pretty good rule of thumb. A reviewer might raise a stink if it's higher than that, because they could say, how do you know you really have what you're claiming you've got? You don't have a very good fit. Okay? So we accept it, and if we zoom in now, again, I hit the peaks and the powder, and see how it's fitting way better now already? Again, I go out to this peak where I was before, where it was not fitting well. Now it's much more centered, right? It's done a much better job because it's changed the lattice parameter. And you can see what it's changed it to just by clicking this. That's obnoxious. So right, here's our new lattice unit cell, right? So it gives all this information here. Okay, let's go back and see what we need to do next. When you refine it, when I made this, I got around 17. We got 16% here, so that was a pretty good fit. So here's what you do next. In the data tree, click on one of the phases in the pattern. This is just looking at your data. Okay, that's how to look at your data and make sense of it. This is for setting the background. Again, we didn't touch the background because it's pretty good, but we can. We can go here to background, and if you wanted to change this or add terms to your polynomial, you could add as many terms as you want, but it's going to not be reasonable. It's usually the case that you can just leave your background polynomial to 3. Unless you've got a really nasty amorphous background that you're trying to fit, 3 is a good number. And there's different types of background polynomials. All these things just create things that look kind of like a background. Chebyshev is the best one to use for sure. Okay? All right. Okay, and this brings us to now the hard part. We've got some peaks that don't fit, and I talked about that. I showed you one where there's clearly an observed peak, but it's not one of our 2 phases that we expect. It's coming from the sample holder. It's actually seeing through it because I had a very thin amount of sample on here. So we need to take care of those peaks. There's about 10 of them, and we need to do something with them. So we've got options. You can either, so we can go home, pull up our data tree. We can go to limits, right? And you can edit limits. You can add an excluded region. The software says right here that you can just select a point on the plot and drag. It does not work. That doesn't work. You can exclude a region, right? You go here, you click somewhere, and like I think that we wanted to throw out, I think it was this one was a bad one. But when I click it, it's not working, right? So we got this to work, Jake and I, but only after like great struggle, like right clicking on the data point somehow made it work. So I'm not going to do that. Instead, I'm just going to fit that peak. I'm just going to make it part of my background, and that's actually not very hard to do. So to do that, we can ignore this now. We're going to go to our background, and right here it says peaks in background. You can specifically make those peaks that you fit automatically, right? So let's zoom in. Let's show you what I mean. Here's our sample. Again, I don't know if I don't see my legend. Let me click phases first, and then the powder tab, and then this shows up. And if you don't see your tick marks, zoom out again. Now grab it, right? So you see, I expect a peak here, and I'm seeing one. This one must be coming from my background, right? So I need to fit that peak. So what you can do is zoom in on it, get a good feel for its position. If you hover over it, you can see down here where the peak position is. Right where I'm hovering, it's at 19.92 theta, right? I should write that down, or just remember it, and then keep track of the approximate intensity. The intensity is about 2,000, thereabouts, right? So I'm going to go ahead and go over to my background, and we're going to say that there's peaks in the background. The first one is located at, I can just type this in, it's located at 19.98, right? And the intensity was somewhere around 2,000, so I'm going to double or triple that. Call it like 6,000. You can leave sigma alone, and for gamma, type 8, okay? Now if we refine this, if we go ahead and hit refine, you'll notice that it's going to actually add a peak there for us, right? If we go to, again, hit phase, hit powder, and there, it's got a peak there for us, okay? We didn't turn on any of our refinements though, so we could make it better if we go to our, no, it's not here. So again, we're going to go to our background, and none of this was turned on to refine. We can now turn it on to refine if we want. We could turn on like gamma and intensity if we wanted. We could even refine the position. You don't want to start with position, you want to give it a good one to start with. But now if we run it again, it's going to fit it even a little bit better. Or blow up. Looks like it fit it. Okay, again we go, and it's fitting it even better, right? So that's good. That it's basically saying we know that this is not one of the actual phases we want to refine. We should treat it like background. So it's just treating it like background. It's putting a red line right through it. Okay. So we would go through and we do that for every one of these peaks that we don't want. So in our case, there's 10 of them. I'll just show you one or two on how to do another one. Again, on this one, I hover over it to get the close to the right position of this thing. That's happening at 32.92. So come over here. We're going to add a peak to our background. Go to 2, happening at 32.92. I give it the approximate intensity doubled to tripled, so the value is like 2,500. Call it 5,000, right? And then put in 8 here for gamma. What's sigma and gamma? That's just a parameter that more or less picks how fat this peak is, right? So this is totally just a mathematical model that's fitting the background. And it turns out, at least I've noticed, that you plug in, it starts at 0.1, but if I plug in 8, 9, 10, it generally fits a little bit closer. You can try other things though, right? So you can turn on intensity refinement and gamma, but I would leave position refinement off for a moment. Okay, you come up here to calculate, refine. Got a little bit better. Double check to make sure it didn't do anything crazy. Yeah, it's fitting it better. And again, you could make it even better by hitting this position refinement flag now, and it's going to move it just a little bit better, right? So you keep on doing this. I'm just going to show you one more. Let me show you a harder one. There's 2 here that you could fit, right? You could fit 1, 2. Let me show you a harder one. One of these overlaps with an existing peak right here, right? You've got one peak that should be there and one that's background, so you can still fit it. Just find the position, 44.65. Right? Give it the intensity, something like 10,000 maybe. Find that, make this 8. And it'll even fit those where there's overlap. And you notice our weighted residual is getting lower and lower and lower, right? So you go ahead and do this. You keep on doing it until you've deleted all the peaks that are not supposed to be there, okay? We still have a problem though. Our weighted residual is still not as low as it could be. Even if you get rid of all these peaks, it's close to 10%, but it could be a lot better. This one refines clear down to like 5% if you do it right. And the reason why is because our peak shape that's calculated is not fitting what our real peak is. So we need to change the shape of our peaks. Let's talk about how you do that. Okay, so once you've finished all of your peaks, so step 15 talks about fitting the peak shape. You go to data tree, powder, and then go to instrument parameters. The shape of the peak generally comes from the instrument, and it can also come from your sample, but fitting it with the instrument parameter is the easiest way to fit it. So we're going to come here, instrument parameters, and there's this U, V, and W. Those are the 3 big ones, U, V, and W. Those change the shape. The order that you do them is usually you fit U first, this first one, U, then you do W, and if you want to, you can fit V, but it's squirrely. So start with U, and it makes the biggest difference. So we're just going to hit the refinement flag just for U. If you turn both of these on, in fact, general rule with Rietveld refinement, the more variables you turn on at once to try and refine, the higher the likelihood that it goes crazy, and you just lose it all. So it's safer to turn them on one at a time. Go here to calculate, run refinement, and look how much better, like drastically better. We're down below 10% now. Our error is still coming from those peaks that shouldn't be there, that we haven't finished fixing yet, so it's going to be a problem until we fix those. But let's zoom in now on some of the ones that we've corrected. Right, they're fitting way better. The shape of these peaks is looking a whole lot better, right? There's still some error, right? The peak shape's not exactly right yet, but here's our difference curve. It's looking pretty good. The main error is coming from the shape of these things. Again, you could go through, you could turn on W, you could continue to tweak your background a little bit, but that's the main approach, right? At this point, we're already getting pretty close. And again, if I were to turn on, let me open another file. Let me just save this one real quick and open the one that I did earlier, which was, I don't remember which one, maybe this one. Yeah, I fit them all here. So I've actually gone through and fit all of the peaks that I needed to here. So now when I run this one, see how close it gets. Like, I'm clear down at like 4%, right? Almost 5%. Just a really good fit. It's fitting it really well. And at that point, you can then figure out what's the fraction of your 2 phases. I think I'll wrap up just about here, Jeff. We're almost done. So any of these steps that I've gone quickly over, it's all here. It talks about it in full detail here. You should be able to find it in these steps. The last thing is how do you figure out the weight fraction? The way you find that, I wish this was more intuitive, but you actually have to open up the file that you're working out of. So I go to my folder where I'm working. No, it's not this. So for example, me, I'm in C, user, wherever I'm at, G2 Conda, GSAS-II, my work, Cobalt 304, takes forever, right? But you're gonna find the list file, right? For whatever you just ran. I was working in a file called new, and this is a .lst, and my computer already knows to open that with Notepad. So open this up, and this is basically a summary of what the software's done, right? It'll tell you how many cycles you've done, what's your best fit today, what's the scattering factors, like all the stuff that it's telling you what did it use to calculate this refinement. And if you search here for weight, near the bottom, it'll actually spit out the weight fraction for your two phases, right? So for the cobalt 304 phase, we are at a weight fraction of about 60%, and for the cobalt oxide rock salt phase, it's about 40%. So it's a number between 0 and 1, it's a fraction. So that's where you get this information. So right now we know that we have mostly spinel and some rock salt. So you can do this for the other temperatures. Again, this was just for 25 degrees C. There's a whole lot more you can do to make these things fit better, but this is a good starting point. One last thing I'll mention is that as you heat these things up, like we've got data all the way up to 1200 or something. What do we have it to? We go up to 1000 C and then we go back down. What's going to happen to your unit cell when you go up in temperature? It's going to expand. So what's going to happen to your X-ray diffraction pattern? It's going to move towards smaller 2 theta values. But the sieve file that you're working off of, that you're going to keep importing, this was done at room temperature. So you're going to find a problem really quick. If you start to do refinements at these higher temperatures, if you try and just throw this in as your phase, it's going to get a really bad fit. Now normally if you just tell it refine the unit cell parameter, it finds it just fine. But sometimes it's so far off that it can't find it. What do I mean by that? Well, let's say that this is your actual data. Let me scroll down here. Say this is your actual data point, right, for a peak, something like that. Normally, you're pretty close when you input your sieve file. You're like this. And so it knows, hey, if I go that way, I get a worse fit, and if I go this way, I get better, and it finds it. It will happen, I think, on this assignment that I'm going to give you guys, that you are out here with your first one, because it's shifted so much. And then out here, it doesn't know. It takes a step this way, it's like, that's bad. It takes a step that way, it's like, well, that's bad too, because it's still not quite overlapping. And so it might be the case that you have to manually go in and tell this to move, right? How do you do that? You do that pretty easily. You come over here to your data tree, go to your phases, and you can just manually change this number. You know it's supposed to go up a little bit. So it's at 8.08, make it 8.09 and see if it fits better. Don't turn this on as a refinement, right? Unclick that box and so you can manually place it somewhere and see if it fits. Once it overlaps a little bit, you're good to go. Okay? There's a whole lot more here. Obviously, like another problem that you're going to notice when you refine this, and it talks about it in the notes, but the sample stage actually is getting taller, right? There's thermal expansion, so the stage is getting taller. So it's actually leaving the diffraction plane. And so you have to turn on a sample displacement error and refine for that displacement. It does a fine job if you do that. And from that, you can actually back out the thermal expansion of your sample stage. You can look at the lattice parameter change of your sample and figure out what the thermal expansion is from there. So just a ton of information here that would otherwise be lost in a normal scan where you just say, oh, it looks like 2 phases are there and something else. Call it good. There's just way tons more information there. Okay, I chewed up most of our time, Jeff.
Okay.
So I'll let you go now.
We'll go for this quick.